All right, today we are going on an absolutely epic journey. We're heading to the very edge of the universe. And forget rockets and spaceships, okay? Our vehicles for this trip, they're the Hubble and James Webb telescopes. So get ready because we're about to travel across the entire expanse of space and time. So, what's actually waiting for us out there? I mean, is it a wall? A giant empty void? The answer, well, it's probably not what you're thinking. Let's dive in and find out.
Okay, first things first. We really need to get our heads around what this edge even is. Because it's not a physical boundary, you know? It's not something you could crash into. It's actually a time barrier. And it's all dictated by the age of the universe itself.
You see, we all live inside what astronomers call the observable universe. Think of it like this. We're inside a giant cosmic bubble. And this bubble contains everything. Everything whose light has had enough time to travel all the way to us here on Earth. How much time? Well, 13.8 billion years, to be precise. Anything outside that bubble? Its light just hasn't reached us yet. We literally can't see it.
Now, this next part is maybe the most important idea for our whole trip, so listen up. Because light takes time to travel, right? It's not instant. So when we look at a galaxy that's, say, a billion light years away, we're not seeing it as it is today. We're actually seeing it as it was a billion years ago. So, yeah, in a very real sense, our telescopes are time machines. Looking out into space is looking back into time. So you might be wondering, how in the world do we measure these insane distances in time and space? Well, we use something called redshift. Astronomers just call it Z. Here's how it works. As the universe expands, it literally stretches the light traveling through it. This stretching shifts the light towards the redder end of the spectrum. So the more redshifted the light is, the higher its Z value, the farther away and the further back in time that object is. It's basically our cosmic odometer for this journey. Okay, journey time. We're going to start right here at home in our own cosmic neighborhood. And from here, we're just going to zoom out, step by step, all the way to the edge. So our own galaxy, the Milky Way, we're part of what's called the local group, which is kind of like a small town of galaxies. But that little town is just a quiet suburb of a much, much larger galactic city, the Virgo cluster. And right at the heart of that bustling city is this absolute beast of a galaxy, Messier 87. And you've probably heard of it. It's home to the very first supermassive black hole we ever managed to take a picture of. How cool is that? Okay, let's pull back even further. And as we do, something amazing starts to come into view. You start to see that galaxies aren't just sprinkled randomly across space. No, they're organized. They form this vast, interconnected structure that we call the cosmic web. And that Virgo cluster we were just in, it's just one tiny piece of an even more massive structure called the Laniakea supercluster. I mean, get this, it's home to over 100,000 galaxies, including us, all flowing together through space in a region that's over 500 million light-years across. The scale is just mind-blowing. So here's a quick little roadmap for where we're headed next using our redshift odometer to track our progress. We've just passed Laniakea. Coming up, we've got the biggest structures in the universe. Then we'll hit the era of cosmic lighthouses, find the very first galaxies, and finally, we reach the beginning of light itself. So those threads that make up the cosmic web, they're called galaxy filaments. And honestly, their scale is just, it's hard to even comprehend. Take the Sloan Great Wall, for example. It's a chain of superclusters that stretches for more than 1.3 billion light years. For the longest time, that was the biggest thing we knew of in the entire universe. All right, now we're going to push even further out. We're leaving these giant structures behind and heading into a much earlier and, frankly, more violent time. We're looking so far back now that the universe itself was just a teenager. But how do we even see anything in this young universe? Well, we need some serious lighthouses to guide our way. And the brightest lighthouses in the entire cosmos are quasars. These things are unbelievably luminous. They can outshine their entire host galaxy. And what powers them? It's all driven by supermassive black holes furiously feeding on gas. So how does that even work? How does a black hole make so much light? Well, imagine gas spiraling towards the black hole. It forms this swirling disk called an accretion disk. And as that disk spins faster and faster, the friction becomes absolutely extreme, heating the gas up to millions of degrees. All that heat makes it glow with more energy than all the billions of stars in its galaxy combined. It is, without a doubt, the most efficient light engine in the entire universe. Okay, Checkpoint. We've now traveled 8.5 billion years into the past. We're at a redshift of z equals 1. This is what astronomers call the peak quasar epoch. So, why were there so many of them back then? Simple, really. The universe was smaller and way more crowded. Galaxies were bumping into each other all the time, and these collisions were the perfect way to funnel tons of gas down to their central black holes, lighting them up like cosmic Christmas trees.
But you know what? We can go even further. We're pushing past the age of quasars. Now, our quest is to find the very first light from the very first stars. We are entering the cosmic dawn.
This amazing period is called the epoch of reionization. See, before this, the universe was basically dark. It was filled with this thick, neutral fog of hydrogen gas. But then, the first stars blinked on, and their incredibly powerful light started to zap that fog, burning it away and making the universe transparent for the very first time. The lights were finally on.
And this is where the race to the beginning gets really exciting. For a long time, the champion, the most distant galaxy we'd ever seen, was a thing called GNZ 11. It had a redshift of 11.1. I mean, think about that. We're seeing it as it was just 420 million years after the Big Bang. That is unbelievably early in cosmic history. But you know how it is, records are made to be broken. And sure enough, astronomers then spotted another one, HD1, with an estimated redshift of 13.27. Now that might sound like a small jump in number, but it's a huge leap back in time. This pushed the frontier back to just 330 million years after the universe was born. We are getting so close to the very first light.
And the hunt is still on right now. The James Webb Space Telescope is out there finding new candidates in this ancient era as we speak, like one called Galaxies Z13. The amazing thing to realize is that this isn't just history. Scientists are actively mapping this cosmic dawn today, pushing our vision closer and closer to the beginning of everything.
Okay, this is it. We've pushed past the first stars, past the first galaxies. We have finally arrived at the absolute edge of what our telescopes can see.
So what's beyond those earliest galaxies? It's not a wall, it's darkness. A whole era known as the Cosmic Dark Ages. This was a strange time. It was after the initial glow of the Big Bang had faded away, but before any of the first stars had a chance to switch on. There was literally nothing to see, because there was no starlight. But wait, that's not quite the end of the road. There is one last source of light. It's not from a star or a galaxy. It's the afterglow of creation itself. The cosmic microwave background, or the CMB. This is the oldest light in the universe, the very first light, released when the cosmos was just a baby, only 379,000 years old. Over the last 13.8 billion years, the universe's expansion has stretched that light so much that we can't see it with our eyes anymore. It's become a faint glow of microwaves that fills the entire sky in every single direction we look.
So there you have it. The edge of our universe, it's not a wall and it's not an empty void. It's the universe's own baby picture, a perfect snapshot of the cosmos when it was just an infant. This is it. This is the farthest back in time we can possibly see. It's our ultimate horizon. But of course, it leaves us with the biggest question of them all. What happened before that picture was taken?